Thank you all for joining me today. I'm excited to talk about how we can harness the power of vLLM and Ray to transform data classification and annotations using AI. Before we dive into technical details, let's take a quick look at the agenda. We'll start with introduction about what is data classification and annotation, especially in the context of data governance. Next, we'll discuss about AI, particularly large language models, and how they can help with these challenges that we are facing. And we will discuss about few other options, and finally go into why we need to fine-tune and how that will be helpful for these use cases. After that, we'll dive into inference process, and finally, we'll summarize with key takeaways. So some introduction. Data classification and annotations are critical elements of data governance. Organizations today are generating a large amount of data across all parts of the business, whether it is customer data, financial data, or even operational metrics. But this data is only useful if it is organized properly, ensuring it's accurate and easily accessible. Now, what do you mean by that? Well, think about how data is stored in large organizations nowadays. We have thousands, sometimes millions of data sets. Some data sets are well documented, well classified with rich metadata, and some are partially documented, have partial metadata. Well, large amount of data sets are lacking that information. Some industry estimates suggest that small percentage of data sets have rich metadata, and this makes it incredibly difficult for data users and analysts, especially data scientists, to find information they need. And talking about business context, traditional data warehouses didn't support persistent business context. That boils down to important data might be underutilized because it's not easy to discover them. And data privacy, ensuring data privacy and compliance is becoming an increasing concern with more regulations and privacy laws like GDPR and DMA coming into effect. Knowing exactly where the sensitive data is and how it is used is crucial. However, with lack of rich metadata above the datasets, it's becoming increasingly difficult nowadays. To address the challenges, traditional process used to be manual approach, where a lot of teams comes together and document the datasets and annotate the datasets with business context and classify them. The sheer amount of effort required to enrich this data manually is tremendous. And it's simply not feasible to handle this scale with human resources alone. And a lot of companies nowadays, or in recent years, have been putting a lot of effort into this. And we are hoping that with advancements made in AI, especially generative AI, these efforts can be fast-tracked. These are some of the advantages that we are hoping that AI can bring in this field. One is automating. So the large language models, especially Gen AI, can help automate the generation of the rich metadata and take away the lot of burden on the data stewards to manually do all this effort. And AI can help to significantly speed up the whole process. And systems like Ray can really help in scaling up as the data grows with ongoing basis. And it's less error prone compared to manually documenting all of this at the scale that we're talking about. And as the large language models get used to get understanding of the business needs, they tend to generate more accurate recommendations. And finally, AI integration is not just limited to metadata generation, but it has a lot more potential in data field. For example, with millions of data sets sitting in the data warehouse, we can automate the discovery of data sets through natural language. And even text-to-SQL and many other use cases can be implemented. And for all of them, this is the basic. We need to have rich metadata. Let's take a look at some examples. So here the task is to generate documentation for the table called users. There are a few columns in it like u_id, name, address hash. As we all know, we try to make things cryptic, and that's what it is. and few tags are attached to the dataset, indicating that the dataset is highly used and contains PII information. And let's see how the documentation looks like. Well, this is too large. Let me summarize it for you. The first paragraph talks about high-level description about the dataset. It's good to see that the description also includes the tags attached to the dataset. And the next paragraph talks about columns and summary from them. And finally, it talks about use cases. Although if you notice that the model kind of understood that we explicitly asked the model not to generate use cases, it mentioned that, but generating the use cases anyway. So kind of funny. If you give the same prompt to the large language model multiple times, the response might vary slightly, but in rare cases, we see response format itself is completely different. In this example, the same example, but if you look at the response, the first one is high-level description again, and second one is column summary, but in a different way, like actually listing out all the columns and generating rich documentation. And finally, we have tag summary. We used to see use cases there. And even the column summary that we see, think about having hundreds of like 30 or 40 columns for the dataset. And if the model is going to summarize all the columns, the description is going to be too large that it's not going to be useful. And there are more challenges that we are seeing. For example, the U_ID, though it does not specify as unique in the table definition, because there is ID in the column name, the model is kind of assuming that or hallucinating that is a unique data that's being stored in that. LLMs are known to sometimes generate context that seem plausible, but actually false and irrelevant, and that's what we are observing in some cases. And depending on the models that we use, these kind of issues might be more frequent versus less frequent, but it's always there. And prompt adherence. If you look at that, we're explicitly saying do not describe the columns in the table, but it's generating it anyway. And finally, let's look at a different example where we want to classify a column in the dataset. Actor ID in game setting table, we want to classify whether it is a PII data or non-sensitive. In the table definition, it clearly mentions that actor ID is hashed off user ID. Okay, before that, the table is game settings, which stores the settings of users for the games. And there are few columns, but most important one is actor ID, which is hash of user ID. A person who is familiar with organization knowledge, like comprehensive fairness, for example, might treat even the hashed sensitive data as sensitive, whereas the LLMs are often trained on vast amount of data from internet. They tend to be in general purpose. So they lack the business needs or business-specific knowledge that humans have, and they tend to generate responses which are far from the reality. And that's what we are observing here. Instead of classifying the dataset as PII, it's recommending as non-sensitive here. So to summarize, different challenges that we are seeing using the large language models as is they lack the business context, the response formats were inconsistent, and though LLMs are designed to follow instructions in the prompt, they don't always follow that. Because of all these challenges, we see limited relevance in the response that they are generating. There are a few techniques that we can adopt or industry adopts to kind of address these challenges, like few-shot prompting. We can give you few examples in the prompt and try to make the model learn from that. And actually, large language models learn better from the in context. But the challenge that we get into is the prompt or the context window will be too large. And not to mention, in the few-shot prompting helps with steering the model to generate response in specific format. But having domain knowledge is something that we need. There are other ways to do it. For example, RAG. We can generate embeddings for existing data set and document them into and steer them into VectorDB and use the VectorDB to find the similar data sets using different techniques like probably semantic search, and then augment the prompt to the model with that information to gain the relevant business knowledge from the relevant data sets. But the challenge we are seeing is, as we discussed before, only small percentage of data sets have documentation or the good metadata quality. So other ways to address the challenge is probably enrich that information and store them into vector DB and then use them. But again, we will get into the large prompt issues, especially in the data space. We have a lot of information, meta information about the data set that can be used to generate richer recommendations. So finally decided to fine-tune the model. The key ingredient for fine-tuning is training data. However, depending on the use case, generating this data can be quite challenging. For instance, for task of classifying the data sets or the columns, it's quite easy. Like we have existing data set and the classifications are well defined, so we can fine-tune the model with that information. The model will learn from the existing knowledge and recommend and give recommendations accordingly. But in use cases like documentation or annotation in the business data sets with business context, things get a bit more complicated. If we already have data sets that are properly documented, then we can use them as it is, but reality is often far from that. There are many teams working on documenting, creating the data sets and documenting them. So the formats of the different documentation that exist are quite different, and some are well documented, some are partially documented. So when we build a solution that we want to enrich metadata in a large scale, we want to make sure the recommendation or the documentation that we generate are of high quality and uniform format. So what we ended up doing is having offline batch inference job, which basically enriches the existing dataset documentations or the business context to generate richer and more formatted training dataset, and that being used for training. So once we have training data, the rest is standard fine-tuning. We have a training job which basically use this training data to fine-tune the models, the large language models we have, and we use rate distributed infrastructure to ensure that training process scales and is efficient. We originally started with Kubeflow to fine-tune our models. As the complexity and the training data increased, we moved to Ray, and it's been scaling so far pretty well. Once we fine-tune the model, the next is to inference. We'll talk about inference more in detail later. And now we have feedback loop. After inference stage, we enter into feedback loop, where AI outputs are reviewed and validated by data stewards. Either the data stewards approve this documentation as is, if they find it really useful, or make recommendations to that, make changes and then persist them. There are multiple signals that we capture as feedback as part of that. Some of the feedbacks will be used to better train the model in the next iterations, or measure the quality of the models that are doing the inference right now. So with the help of the feedback loop, the model continuously learns. With every iteration of the recommendation it gives and data stewards reviewing it, they continuously improve the accuracy. And it also generates consistent response format. Let's take a look at high-level architecture. Of course, there are more pieces in it, but this is very high level. In the left side, we have the client, which represent end user or the system which is interacting with our AI application. This could be data engineer, data scientist, or business stakeholder who are trying to classify and annotate data sets with business context. And the client submits the request to AI application. And most of the organizations have data platforms built with systems like data catalog, which catalogs and registers all the data set in the organization. It contains information like metadata about the data sets and who is the columns and other information. And in recent years, many organizations started adopting data lineage and data lineage has been tremendously helpful for a lot of privacy and compliance use cases. And there are many more use cases as well. And this is something really valuable, especially in the context of generating recommendations. Since we can derive some useful information from the data sets which were used in producing the data set in question, or the downstream data sets as well. And we have systems like Audi system which capture change events happening on the data set level or the data level, and also the usage information about data sets. And most organizations have classifications, well-defined classification structure, where we want to classify based on that existing structure. So the application kind of, based on the request that it receives, retrieves the information from the existing tools and augments the prompt for the specific use case. And that prompt being given to the inference service to generate the recommendations. In this case, we are using vLLM and Ray for powering our inference. vLLM framework is fast, easy to use library and performs inferences with low latency. Whereas Ray Serve takes care of scaling of these deployments based on the load that the request that is receiving. This allows for the combination of both, allows for high performance and scalable inferencing, which is critical for processing large data sets in real time. And as the recommendations go to the user, we receive feedback from them, and the application starts storing them in the feedback store, which will later be fed into training job. Along with the training data that we talked about earlier, the feedback information is also fed into training job to better train and iterate as people start adopting these solutions. And we are using Ray training jobs for training these large language models. Ray provides high parallelism and ability to distribute workload across multiple nodes. Let's take a look at the prompt again and the responses after fine-tuning. The prompt is quite simplistic that we are seeing here. In real world use case that as I described, there is lineage of data set that can be used. There is a lot of other metadata about the data set that can go into prompt. And we also need to put a lot of effort on making sure that what the information that we give is meaningful enough and it's not too much for the model to start hallucinating or losing context of the instructions that we are giving. Okay, so now it's trying to classify actor ID, which we have seen earlier. Probably the model would have gained knowledge from the existing training data that even the hashed sensitive data should be treated as sensitive, so it's recommending as PII. And if you look at the documentation it's generating, it's more concise and more structured. Now let's talk about inference. So the inference needs for our solution is quite simple. We just need low latency inference for both online single request and batch request. You can take example of our users trying to classify multiple columns at a time or generate documentation for multiple columns at a time. It's quite common. So we have a use case of online and at the same time doing batch inference. And we need high throughput. And scalability is a big thing here because as we have large number of data that needs to be enriched with metadata, and as the adoption grows, the infrastructure must scale and expand according to the load. And the resources we are using are high compute for inference or the training. So efficient use of high computational resources is essential to keep the operational cost low. So we started our inference journey as basic as Olama and ended up with vLLM. And our experience is vLLM scales pretty well. And it also offers low latency thanks to the paginated attention techniques that that's vLLM is using. It also provides OpenAI API spec, so it's much easier to integrate with any of the open source library available for building AI applications. It also has batch inference, and is also quite performant as well. And vLLM supports something, the quantization, and that something is quite helping us and also giving good performance. The quantization kind of helps with keeping the resource utilization low and keeping the cost low. Because when we quantize the model, basically the amount of memory needs and other will reduce, so we can have more inference pods running on the same amount of resources without quantization. On the other hand, Ray Serve kind of takes care of auto-scaling these vLLM deployments based on the request that it is receiving. If you take a look at the right side example, in the top, we are defining Ray autoscale configuration. It's most simplistic one, but we can also add health checks and other stuff. Here we're indicating that the minimum replicas for our deployment is 1, and max replicas that go up to is 10. And we are kind of indicating that target request for each deployment is 5, and then each can go up to 10. So based on the request that it's receiving, Ray kind of takes care of auto-scaling these deployments, and if the request comes down, and it shrinks down the deployments as well. And we can have a simple Python-based, fast API and use the easy-to-use vLLM libraries to create this deployment, as we are seeing here, and then configure that with Ray. It's quite easy to scale from local into the production with minor changes in the configurations of auto-scaling, Ray auto-scaling that we need to do. And Ray also supports health checks and auto-recovery. So like the amount of time it takes to productionalize the inference from local into prod is tremendous here. Okay, let's summarize with key takeaways. Accurate classification. One of the most significant benefits of AI-driven data classification is accuracy. With fine-tuning the models, we can ensure that the data sets are accurately classified based on the patterns and contextual understanding. As models give recommendations, get trained on the feedback, the accuracy improves over time. And scalable classification. With help of GenAI and frameworks like Ray and vLLM, we can scale the complex problems like data classification annotations easily. And reduced toil. By automating the process of classification annotation, we can significantly reduce the manual effort and toil required by different teams in the organizations. And this is cost effective, as automating the data classification and annotations with AI can reduce the manual effort required and save the operational cost. As we wrap up this session, I want to emphasize that by harnessing the power of AI, we are not just solving immediate challenges, but we are setting the stage for more data-driven future. Thank you all. I will open up for questions.
How many examples do you have to give for fine-tuning for your?
Good question. So it depends. For, let's say, dataset documentation or the classification is completely different. So if you talk about, as I mentioned, like we have few percentage of datasets are well documented. So we kind of generate enriched training data from that and document. I would say like probably about 10% of the datasets that we have went into the fine-tuning model.
A couple of questions. You mentioned about data lineage. Are you using any specific tool for data lineage?
So yeah, we have some solutions that are inbuilt that we're using for data lineage, and yeah, that much I can talk about.
Okay. So nothing open source as such. You built something in-house, yeah?
I prefer to stick to this talk.
No problem. You also mentioned about Ray and vLLM. Is there any specific platform that you're running, Ray and vLLM, for scalability and everything?
Yeah, so we have inbuilt solutions for launching Ray. We have infra team which takes care of our Ray as offering, and we launch the clusters as we need, and then run the jobs and scale the deployments or training jobs that we need. Good question.
Any further questions? Please raise your hand, then I can give you a microphone. If no, then let's thank the speaker again.
Thank you all.